Alright, I think I got everything dialed in and set up. Well, you guys got a quiz Tuesday, it's looking like, so let's review. First things first, it's about derivatives of trig functions, so we got to make sure you know all six of those. First two should be a piece of cake. We know the derivative of sine is cosine of x. We know the derivative of cosine is negative sine of x. The other four, hopefully you have them memorized by now, but more than just having them memorized, you also better be able to sort of show where they come from. So I'm going to run through that too. So the derivative of tangent is, I haven't really studied, I don't really remember, secant squared, right? Okay. Hey, pretend for a moment I got that wrong. Well, you should know how to figure out where that came from. So if you don't remember the derivative of tangent, and you've got 3 minutes, then you should be able to grab tangent and say, well, you know what? If they want me to do the derivative of tangent, I can always rewrite tangent as sine over cosine. And then I can do the derivative of this using the quotient rule. Quotient rule, of course, says do the derivative of the top, so that gives you a cosine. And it says multiply that by the bottom, so that's a second cosine. Then subtract the top, which is sine, times the derivative of the bottom, which is negative sine. And that whole thing gets divided by the bottom squared, so cosine squared. So this whole big mess is the derivative of tangent, but we'd have to clean this up. This is giving you a cosine squared. Now we're subtracting a negative, so that'll be expressed as plus. Sine times sine is sine squared. So I know I told you last week, Friday, that we could sort of downplay these trigonometric identities, but something like cosine squared plus sine squared being equal to 1, I 100% expect you to remember that and utilize that. So that gives you 1 over, oh, this is supposed to be squared, by the way, forgot that for a second. So this is giving me 1 over cosine squared. And one other trig identity I do expect you to remember is your reciprocal identities. So if I want to just kind of rewrite this, instead of 1 over cosine squared, I can make it secant squared. And that's certainly where I would expect you to land. So that's that. Now, of course, you should just have this memorized because 99.9% of the time you're not doing this work to find the derivative of tangent. You just know it. But there is going to be one question on the quiz where, for sure, I'm telling you to derive the derivative of either tangent or cotangent or secant or cosecant. So I don't really feel like going through all 4 of them right now. Hopefully having run through tangent will kind of jog your memory. But yeah, let me give you the other ones at least. For cotangent, we did talk about how since tangent and cotangent are cofunctions, their derivatives are also just cofunctions. So if this one's secant squared, this will be cosecant squared. But of course, when you take the derivatives of these cofunctions, they tend to give you negative derivatives, so you can remember that. Then for secant, the derivative of secant, a little bit weird. Derivative of secant is secant itself, but then multiplied by tangent. So you get secant times tangent. Then the cofunction of secant would be the cofunction here. It would be cosecant and cotangent. And again, since we differentiated a cofunction, we're going to get negative. But that's it. There's all 6 of your derivatives. Now I went through where the derivative of tangent came from. Why don't I also go through where the derivative of cosecant comes from? And then I'll leave it to you to figure out the other 2. Or to ask me about it in class. Or to ask me about it during advisory. Or to ask me about it after school. But you got tons of opportunities to hit me up if you're not sure. But looking here, if I was trying to do the derivative of cosecant, and again remember, the only time you're ever going to do this is when I specifically say, show me where the derivative came from. Otherwise I would just expect that you knew it and you wouldn't have to show any work. But if I said to you specifically, where does this derivative come from, then you would rewrite this as instead of the derivative of cosecant of x, you'd rewrite it using the reciprocal identity. We'll call this 1 over the sine of x. And then I would probably just do this as a quotient rule problem. Derivative of the numerator would make 0, which times sine will of course be 0. Then we subtract from that the numerator times the derivative of the denominator, which is negative, nope, positive cosine, of course. And this is going to be all over sine squared. Okay, so this means that in our numerator we just have 0 minus cosine, or negative cosine. In our denominator is sine squared, but sine squared means that you have a sine of x times a sine of x. And you probably want to literally see this as two separate factors, because what we would do now is, in the numerator, cosine, of course, if there's nothing else up here, we could pretend that there's a factor of 1. And this negative sign here, we could also pretend that that's just sort of a factor of negative 1 that we're multiplying the whole thing by. And so when you look at this now, what you hopefully see is three things. We've got a negative 1 factor. We've also got a factor of cosine over sine. We've also got a factor of 1 over sine, which means by the time all is said and done, we can call this negative from our negative 1. 1 over sine is our cosecant, and cosine over sine is our cotangent. So by kind of splitting the bottom into two separate factors of sine, and letting one of those sines combine with cosine using the quotient rule, we get cotangent. The other sine combining with a factor of 1 in the numerator, we use the reciprocal identity, we get cosecant. And of course we had a factor of negative 1 as well, that just makes the whole thing negative. But there's your derivation that explains why the derivative of cosecant is negative cosecant times cotangent. Okay, so hopefully that's kind of helpful. Now let's do these 12 actual practice problems. Notice these 12 are from the day 2 activity. There was also a day 3 activity. That was the green sheet. So right now we're on the white sheet. Okay, so like I said, this is the white sheet. If you're wondering, I do have the green sheet problems as well. I'm sure I'll post this as a second video. So you'll have a video 1 where I go over the 12 problems from the white sheet, and then you'll have a second video where I go over the problems from the green. So if you're waiting on the green problems, wait a little longer. That video will come out soon. But let's start with the whites. And again, I would recommend pretty highly that if this problem is not showing any parentheses at all, you should probably show them to remind yourself what's happening here. And I would say that we can pretty safely say we are taking the sine of that whole expression there. We're taking the sine of the 2x cubed. So that means if I go to find f prime, remember you do have to actually write this. A lot of you guys like to dive right in and just start differentiating the function, but you have to use proper derivative notation on the left-hand side of the equation too. Make sure you keep this as an equation. But as I see this, this is definitely an inner-outer function problem. So I definitely want to differentiate this sine expression and then chain rule out the derivative of the inner function. And that's it. So the derivative of sine will be cosine. We said when you're differentiating the outer function, we just leave this inner function alone. And it's only when we're done differentiating that outer function that we now chain rule out the derivative of the inner function, which is just a power rule problem. 2 times 3 is 6, and you take 1 away from 3 to get 2. So we get a factor of 6x squared. And I want you to clean your answers up, but there's not a heck of a lot you can do here. All you're going to do is take that factor of 6x squared and pull it in the front as a coefficient. So your final answer should be 6x squared times the cosine of 2x cubed. But that's it. Number 1 is pretty straightforward. And number 2 is pretty similar. It's almost identical because, again, I would say that the parentheses go right here. So again, we just have an outer function that is our tangent trig function. Inside is 5x cubed, which is just sort of a plain polynomial function. So if I go to do the derivative, I'll get a y prime that equals the derivative of tangent. The derivative of tangent is secant squared. But again, leave the inner function alone. So just leave it as 5x cubed. And then from here now just chain rule out the derivative of that inner function, which will be 15x squared. And finally, your final answer, you'd want to take that 15x squared again and just bring it to the front as a coefficient. So you get 15x squared times secant squared of 5x cubed. And there's nothing more we can do to simplify that. This right here is our best answer. So let's take a look at 3. 3 is pretty similar from the last ones too. Again, you've just got an outer function that is your secant trig function, inner function is a polynomial. The one thing that's a little different this time is when you differentiate secant, you do get secant times tan. So you have two different trig expressions. So what goes inside the secant function here? Well, I hope it's obvious that it's still the whole 4x to the 5th. And what goes inside this trig function here? Well, it should be the same stuff. It's not like this is simpler or more complicated. It should just still also be 4x to the 5th. Now we've got the inner function to deal with, so we chain rule it out. Now, do I chain rule out from the secant and then also chain rule out from the tangent? And the answer is no. Remember, we're chain ruling from up here. If we did ddx on this whole thing, then we're only differentiating this expression. And so you only chain rule out the derivative of that thing once from the beginning. It doesn't chain rule out twice from these two factors, so don't get that confused. So by the time we're done, we'll have a 20x to the 4th. And we can't really clean this up much, so we'll just say y prime. We'll bring the 20x to the 4th to the beginning like we've been doing. And then secant versus tan, it doesn't matter. You could put those in either order, but I'm going to go with secant 4x to the 5th. And then times the tangent of 4x to the 5th. And I'm going to leave these parentheses in place. I know the problem doesn't give parentheses, but we should probably get in the habit of always using parentheses so that we're never not sure about what we meant. Let's look at 4. 4 is not a heck of a lot different either. I thought it started to change, but no, this one seems about the same too. Alright, so one more time. Again, it's just an inner-outer function kind of thing. So we go y prime. Derivative of cosecant is negative cosecant times cotangent. And again, they both get the same inputs, the 5x to the 5th that we're leaving alone. But then we do also chain rule out the derivative of that 5x to the 5th, giving us a 25x to the 4th, which, as a final answer, keep the negative sign, bring the 25x to the 4th to the beginning, so it's negative 25x to the 4th, and then times the cosecant of 5x to the 5th times the cotangent of 5x to the 5th. And there's really not much more we can do with that. That's our best answer right there. So looking at 5. Alright, so 5 is finally pretty significantly different from the others. For sure you should look at this and say that this cosine, we're taking the cosine of the x squared. Then looking at the whole thing, you should see that what we've got here is this polynomial, 2x to the 5th plus 3, times the cosine of x squared. So this thing for sure we need to treat as a product rule problem. So if I kind of highlight this, our first factor is the blue, and our second factor is the orange. So if we go to do the product rule on this, then the product rule says to do the derivative of the first factor. So I'm differentiating the blue to get 10x to the 4th. But then I multiply that by the orange, just left alone, just bring it down. So just the cosine of x squared. And again, we're just multiplying those guys. Then product rule says we're going to add to that the blue function this time, left alone, 2x to the 5th plus 3. But we want to multiply that by the derivative of the orange. Now the orange is another nested function. So if I do the derivative of cosine, I get a factor of negative sine of x squared. But now that x squared is an inner function, so I have to multiply by the derivative of that. So only here do we have a chain rule that we worry about, and it pops out a factor of 2x. So there's sort of everything. And we'll clean this up the best we can, but again, there's not a ton we can do. I've got a 10x to the fourth as a coefficient on a cosine of x squared. Then over here, we could at least borrow this negative here to let this whole addition problem become a subtraction problem. Then I could take the 2x and distribute it through here, but we tend to want to keep our answer simplified, so I think really I'll just take the 2x, have it come first. Then I'll take the 2x to the fifth plus 3. And then we've got our sine of x squared. But I think this is basically the best we can do, because if we took the 2x squared and tried to distribute it in, we would kind of want to just simplify it again right away. If we distributed everything, then we would have, what, a 10x to the fourth times the cosine of x squared. If we went distribute, then all I would have is a couple of sine expressions that I couldn't really combine anyway. Like, what would we get? If we distributed sine, or 2x sine of x squared, we would get 4x to the sixth times the sine of x squared. And if we distributed 2x and the sine of x squared onto the 3, we would get minus 6x sine of x squared. But what does that do for us? Nothing, really. Because these two terms here that we just made, they don't combine with the other one over here. So by distributing everything out, I haven't opened any doors to simplifying anything. And instead, I would just look at this again and realize that I think because I've got a sine squared and a sine squared, I just want to factor that back out again and keep it simple. So none of that distributing is helpful. You literally just want to stay here at the purple. And even though it doesn't look like much, that's the best we can do. We just can't clean it up beyond that. So we won't. We'll stop right there. Alright, doing 6. So 6 is a quotient rule problem. And of course, inside the quotient rule problem, we've also got a chain rule problem, because we've got that nested function down there in the denominator. Is there anything I could do to make this a little bit cleaner? We could factor out a -1. I'm not sure you guys would be big fans of that, though. We would have a 2x squared plus 5 in the numerator. So technically, if I wanted to, I could factor out that -1, and then by the constant multiple rule, I could factor out the -1 and then do the derivative on this whole big quotient rule problem. But again, I don't think that's worth it. You guys can probably just do the derivative as written and just be careful with the negative signs, right? But if you wanted to, you could kind of strip this of all of its negative signs, differentiate, and then just multiply again by the negative at the end. That just doesn't seem smart to me, though, so I won't bother. I'm just going to do it as written. So, starting over. Alright. Again, for quotient rule, we know that we're just going to want to be doing the derivative of the top times the bottom minus the normal top times the derivative of the bottom all over the bottom squared. So what's the derivative of the top? Well, it would be -4x. And that's it. And the bottom is the cosine of 2x cubed. Then the numerator is the -2x squared minus 5. And the derivative of the cosine of 2x cubed, I'll probably need more room for this because we have to do chain rule. But what's it going to be? It'll be negative sine of 2x cubed, but then times the derivative of that inner function, so times a 6x squared. And then, of course, down in the denominator we get cosine of 2x cubed squared. Alright, so again, the question is, could we clean this up at all? And we mostly can't clean it up, but we sort of can. So from this first term, I can't do much. It'll just be negative 4x cosine of 2x cubed. But we did say that over here, if we're very careful, we could let this negative sign just turn us back into a plus sign. But then this thing here certainly has a negative we want to factor out. This could be negative 1 times just the 2x squared plus 5. And so now we're letting this negative sign turn our plus back into a minus. So we're still subtracting, but it's a slightly simpler expression. We can just use the positives here. The 6x squared is going to come over 2, but we're subtracting the 6x squared times 2x squared plus 5 times the sine of 2x cubed. Okay, could we clean this up anymore? Again, the only thing I might do is factor out some GCFs. So I see a negative and a negative. I can definitely factor that out. I see a 4 and a 6, so I could factor out a 2. I see an x and an x squared, so I could factor out an x. Anything else coming out? I don't think so. So if I factor out a negative 2x, then I'm left with what? 2 cosine of 2x cubed? And we're factoring out a negative, so the minus becomes a plus. We're factoring out a negative 2x, so this will be 3x. Nothing got factored out of here, so 2x squared plus 5. And then a sine of 2x cubed. I think that's about the best we do here. And it ain't pretty. I know it ain't pretty. But it's the best we can do. So that's that. That's 6. So 7. 7 is another good one. For 7, you're going to want to remember that sine cubed. What that means is we are taking the derivative, or we're taking the sine of x to the 5th first, and we're cubing last. So remember, sine cubed of x to the 5th literally means do the sine of the x to the 5th first, and when you're done doing that, go ahead and cube everything. So this for sure is a nested function. In fact, it's 3 nested functions, because our outermost function is this here function that cubes. Then the next layer in is this function here that takes the sine of stuff. But there's a third function, the one on the inside, the one that takes numbers and raises them to the power of 5. So there's that. So differentiating this whole thing in order would mean differentiating the cubic function first, which just gives 3 times some stuff to the power of 2. Oh, by the way, what's the stuff? The stuff is the sine of x to the 5th. Alright, so now, this should have been orange, by the way. But now that I've differentiated, I have to multiply by the derivative of the inside function. So I now have to multiply by the derivative of the sine function, which of course is just the cosine of some stuff. What's the stuff? The x to the 5th. But now that I've differentiated that, I now have to chain roll out the derivative of x to the 5th. So out pops 5x to the 4th. But there's your fully expanded derivative. We're differentiating the cubic function first, then we're differentiating the sine function, then we're differentiating the x to the 5th to get all these parts. And then we just want to put all those parts back together again. So surely coming first would be any constants or simple polynomials, and those two guys combine, so that's 15x to the 4th. Then if everything else is trig expressions, then do the higher power ones first, because sine squared, we certainly want to rewrite that as sine squared, where the 2 is on the sine function. So it's sine squared of x to the 5th, and then times cosine of x to the 5th, And I guess I would say stop there. Although, could we do a little better than this? You know, I'm gonna do a little more, and if you're afraid of my confusion, then just fast forward. But here's another trig identity we probably should definitely know. So what is it? I mean, we know that sine squared plus cosine squared is 1. That's the famous Pythagorean identity. But that does mean that sine squared alone, sine squared, is 1 minus cosine squared. So we can always use Pythagorean identities to rewrite sine squared expressions as cosine squared expressions, or to rewrite cosine squared expressions as sine squared expressions. So thinking about that, are we going to be better off if instead of a sine and a cosine, we just had all cosines? And the answer is yes, that is considered better. So even though I would definitely let you stop here at the purple, for anyone who gives a darn, we could go a little further. We could go a little further by keeping this 15x to the fourth, but then using this alternate form of the Pythagorean identity to rewrite sine squared as 1 minus cosine squared of x to the fifth times cosine of x to the fifth. Now this doesn't look like much, but from here I could now sort of distribute everything in. So I'm distributing in the 15x to the fourth and the cosine. So when I distribute both of those things onto the 1, I get 15x to the fourth times the cosine of x to the fifth. Then I distribute both of those onto this guy, so I get minus 15x to the fourth times cosine cubed of x to the fifth. So if everything's distributed, is that good? No, that's not really good, because we would want to just factor our common factors right back out again, wouldn't we? So what would that look like? I think really what we should have done is probably just taken that guy, stuck him in the middle, right there. So I'm running a little bit out of space, but I'll scroll down. I think our final best answer was to just keep the 15x to the fourth factored out. And also to keep the cosine of x to the fifth factored out. But then have that getting multiplied by 1 minus cosine squared of x to the fifth. So technically this green answer might be a little bit better than this purple answer, but only because the purple has two trig functions in it, sine and cosine, and one is squared, the other one isn't. This one still has one function squared and one function that isn't squared, but they're both cosine. That's technically maybe a little cleaner than the purple, but I wouldn't expect anybody to do that. The purple is just fine. And then the purple doesn't include a binomial either. When we use Pythagorean identity here to turn sine into 1 minus cosine, that's not the best move in the world because it does end up giving you a binomial where we didn't have a binomial before. So there's a lot of kind of weighing what's better here. And I don't know, if I was forced to make a decision, then maybe the purple is actually better than the green, who knows. So for sure, stop at the purple. Stop at the purple, don't go on. Okay, moving on. Number 8. Number 8, we're back to sort of a nested function. It's a little confusing because we've got the 2 here. So the big question, of course, is, what are we saying? So let's take a look at 2 completely different problems. Imagine if you had both of these. And imagine if this guy had a set of brackets here, telling me go ahead and do the cosine first and wait to square everything at the end. Or if I had this expression here, where it says do all this stuff, square it, and then take the cosine. Hopefully you can tell that those two derivatives will be very different. Here, we would do power rule first, then we'd differentiate cosine, then we would still chain rule out the derivative of that inside function. Over here, we've only got a couple of nested functions. We would differentiate cosine first, then we'd differentiate the stuff that's getting squared, then we'd chain rule out the inside stuff. But these two things are very, very different, so which one is right? Well, this one is right, because over here, if we had the cosine all squared, they would have written it as cosine squared of the negative 3x squared plus 2. So we sort of already have a way to express what this one over here is trying to express. So I would say that's just not the right interpretation of the problem. This one is. So looking at 8. Looking at 8, we know that we want to treat this as a function whose outermost function, because we said the parentheses go here. So the outermost function is the cosine function. Then when you get to the inside, there's a negative 3x squared plus 2. And then there's that function squared, of course. And so it's that function getting squared that sort of comes second, actually. But yeah, so doing this, we would differentiate the green first. So it's the derivative of cosine. It's sine, but negative sine. And then leave the inside completely alone. So negative 3x squared plus 2, all squared. Now, we just finished differentiating that outermost function. So now we can multiply by the derivative of this inner blue function, which would just be power rule. So you multiply by 2 to get a coefficient on the negative 3x squared plus 2, whose power then drops down to 1. And we still chain rule out the derivative of that, though, so we get a negative 6x for our troubles. Then what happens? Nothing? I think we're done. Yeah, those are all the pieces. So now just try to put this together. For sure, we're going 2 times negative 6x and borrowing the negative from here, letting those two negatives cancel. So where are we at now? 12x as a coefficient. Then we've got this polynomial, the negative 3x squared plus 2. Then we've got the sine expression. Can we do much better than that? I don't think so. So the one thing we could do, which I'm a fan of, is getting rid of these leading negatives. Sometimes you can't exactly avoid it, but I'd rather see this negative get factored out and attach itself to the 12x. And then this would be rewritten as 3x squared minus 2. And then the slightly weirder news is within the sine function itself, I could factor out a negative again, but notice it is going to factor out into these brackets, so you get like negative 1, 3x squared minus 2, and then what you're squaring is this whole thing. So when I square the negative 1, I just get 1, which means it kind of just goes away, and I'm back to squaring that thing. So maybe our final best answer is to stick our negative on our 12x, because we factored a negative out of here to just get 3x squared minus 2. Then we're now taking the sine of, well, the negative again got factored out and turned positive, so we're just still doing the sine of 3x squared minus 2 squared. So to me, that's the best looking version of our answer. We factored negatives out of these binomials. We now just have one negative on our coefficient, which is a little bit cleaner. And that's it. I think that's the best we're doing. So that's the end of 8. Looking at 9, however. 9 is not so bad. 9 is another nested function for sure. Pretty much every one of these is going to involve chain rule. I don't know if I'm sitting right. I feel like I'm cutting my face off, but that's okay. Nobody's looking anyway, probably. So how's this go? Y prime would equal. Well, the outermost function is just the squaring function, so I guess I would multiply by 2, get a coefficient of 2, leave the base alone, 1 plus cosine of 3x, it's in parentheses like that. And this power of 2 drops down to 1, so I just won't even write it. But there we go. That's the derivative of the outermost function. So now we got to multiply, chain rule out, the derivative of the inner function. And to differentiate this binomial, you technically do differentiate 1, which gives 0. And then you add to that the derivative of cosine of 3x, which is negative sine of 3x. And then from there you chain rule out a factor of 3. Then I think we're done. I think we're done differentiating now. So nothing left to do but clean this up. So what would this look like cleaned up? Surely the 3 and the 2 multiply to make 6. Then this is a binomial because it's got 2 pieces. This is technically not really a binomial because 0 plus negative sine of 3x is just sine of 3x. So I think because this is a monomial, I'd have it come next. Oh, yeah, we got to pull the negative sign off it. Just make this a negative 6. Then that'll be negative 6 times the sine of 3x. And then times 1 plus cosine of 3x. But that's going to be in brackets. And that's it. You can take those parentheses away. But what does this look like? Looks like this. We can't do much better. I'll keep trying to do it. I can do a little better, so you know what? I'm going to try, just for anyone who wants to learn a little more. What if we took this and distributed? We would get negative 6 sine of 3x minus 6 sine of 3x cosine of 3x. Well, by distributing, you may now be noticing that right here, we've got the makings of a double angle sine identity. Remember, the double angle sine identity said that the sine of an angle that's getting doubled can break down to the sine of just half the angle times the cosine of just half the angle, but that whole thing is doubled. So if you ever see a 2 times a sine times a cosine, you could technically simplify that, and that is what I see here. Well, it's what I see here if that 6 was sort of separately a 3 times a 2. So I can borrow that factor of 2 to clean this up. Now what is that going to bring me? It looks like it's going to bring me to a negative 6 sine of 3x minus 3, and then all these 3 pieces get combined, and it just becomes the sine of a 3x that got doubled, so it's 6x now. And oh, by the way, I can factor the negative 3 out now to just have negative 3 as a coefficient on a sine of 3x minus the sine of 6x. And I don't think there's much more I can do from there because sine of something minus sine of something else, unless the 2 expressions have the same thing in parentheses, you really can't simplify them. I don't think there's any rules for, well, I mean, that's a lie. Of course, there's some rules, but the rules that we know are only for when you've got the sine of something and the sine of the same thing, or the cosine of the same thing. But since I have a 3x and a 6x, it's not going to work. So again, I hope you guys are understanding me and not getting confused, but I'm saying all this stuff in the green box is fine. If you stopped at the green, I wouldn't be mad at you. But hopefully when you look at the green versus the burgundy down here, I hope you're seeing that the burgundy is a little cleaner. So there. Oh, actually I screwed it up, didn't I? There should be a factor of 2 here. If I factor a 3 out of the 6, I still have a factor of 2. Okay, whatever. That's 9, doing 10. Okay, 10. So 10 is interesting. When you look at 10, I'm sure the first thing you would do is rewrite sine of x as the sine of x all cubed. You put 3 on the outside. Now we're multiplying by the cosine, which means this problem is certainly a quotient problem, where the first function is sine of x cubed. The second function is just a trig function. So if I go to do this derivative, I still got to do product rule. So I know it's going to be derivative of the first times the second plus the first times the derivative of the second. So we're differentiating this first guy. Derivative of sine is cosine. Oh, no, screwing up already. It's the cubic function first. The cubic is the outermost thing. So you'd multiply by 3. You'd get 3 times the sine of x. And that would still be getting squared, the sine of x. So that's the derivative of the first. Do we have to chain rule anything out? Well, yes, we do. We have to chain rule out the derivative of sine, which is another factor of cosine. But then we also have cosine, because cosine is our second function. So we now have another cosine. Then over here, we just bring down the sine of x cubed. And multiply by the derivative of cosine, which is negative sine of x. Alright, start cleaning up. This is going to be what? 3 sine squared? Cosine squared? And this is going to be minus sine to the 4th. So what can we do to that? Well, we could factor out sine squared, and that seems to be the only thing. So we would get sine squared of x times 3 cosine squared minus sine squared. And that's it. So that's 10. Let's try 11. Okay. 11 threw some people off in class because I think they kind of forgot the rules, but wouldn't y prime just be the derivative of this whole thing, technically, 4 sine squared x plus 5 cosine squared x? I'm writing kind of fast because you should know this already. But if you want to do the derivative of a sum, then don't we just break that down and say, okay, do the derivative of just the 4x squared, the 4 sine squared of x. And then you just add to that the derivative of the second term. So, oh no, am I making a mistake here? No, I'm not differentiating yet, so I'm just bringing these down, 5 cosine squared. Okay, and then next, another thing you might have forgotten is that these coefficients, you can just pull them out, right? So we're really just doing 4 times the derivative of sine squared and here we'll do 5 times the derivative of cosine squared. Alright, again, none of these steps are steps you needed to show, really. You could probably just do this straight up from the beginning, but as long as you understand why, that's a good thing. So what's happening here? Well, you certainly could just be treating this as 4 times sine of x squared. And I think I probably would recommend that you do that. So just kill this 2, bring a 2 out, And there's your new expression, which is sort of easier to differentiate because if I differentiate this, I just do power rule first. 2 times 4 makes 8. Leave my base alone, sine of x. Subtract 1 from my power, it goes down to 1. And then chain rule out the derivative of the inside, which is a cosine. Now, we're going to add to this the 5 one, which again, you could probably just be thinking of as 5 as a coefficient on a cosine function that's getting squared. So if I do power rule, I get 10 cosine of x to the 1. But then I also get to multiply by the derivative of the inside, so I get to multiply by negative sine of x. And now that we've got all this, time to play cleanup. This is looking like 8 sine x cosine x's. And then it's minus, so minus 10. And technically sine x cosine x's, I would flip these. Just because we already have sine and then cosine, we want to continue having sine and then cosine. Because that helps us recognize our like terms. Which, by the way, these are like terms. So this is negative 2 sine x cosine x. And that's about the best you can do. If you stopped here, I wouldn't be mad at you. But you should probably be noticing that this is the same identity from before. This one. It said that 2 times the sine times the cosine can be turned into the sine of the angle doubled. So this is a pretty obvious case for doing that. This is now negative sine of 2x. So if you can do that, you definitely should. But if you did this, this is okay. Alright, one more problem. I'm running out of steam. So for number 12, same basic idea. Just to differentiate, go ahead and differentiate this first guy, which would be 2 times secant tan. And then you differentiate tan, so just plus the derivative of tan, which is secant squared. And then, not a heck of a lot we can do here, but we could factor out a secant. And that'll leave us with a secant of x times 2 tan x. Yeah, plus a secant. I think that's it. Okay, got tired there. Yeah, I'd say that's the best we can do, other than this needing to be a bracket. Alright, hopefully that was helpful. I think it's time for me to go. But I hope you guys get a chance to watch this and learn something from it. Thanks. Bye.